I know the screen is not lowered. Go. Yeah, I think I started the recording. Let me double check. Yep. So it's streaming already. It's right here. It says stop streaming. So when I press the button again, it will stop. All right. So just minimize. And this is the Monday, Wednesday class. Did you guys have a good Labor Day weekend? Did anyone do anything about labor or union work stuff? No? Okay, well, I was at the union picnic in Land Park, so that was kind of cool. Free food. I'm good for that. I was actually manning the union table for LRCFT, the Los Rios something of for teachers. It's the union for all the professors, part-time and full-time. So it was kind of cool. I took a picture with Richard Pan, the politician. Okay, he stopped by the booth and I didn't even know who he was. And then somebody said, "Oh, that's Richard Pan."
He's a representative state.
Yeah, I think so. So Dr. Richard Pan. But if I call him Dr. Richard Pan, then he will have to call me Dr. Aoyong as well. So we're even. I didn't even recognize him in person. So that's him, taking pictures with other people. Kind of interesting. So I can try to push for that, binary. Haven't talked to him about that yet, but that's on my mind. I got his picture now. I can tell people we were just talking about binary numbers in elementary school. All right, so what we're going to do today is we are continuing to talk about binary numbers. Okay, so we are now pretty much done with base conversion. So we'll start with binary number addition. So we're going to look into how do we add numbers, but not just any numbers, not base 10, but base 2 numbers. All right, so let's go ahead and start with this. Are there any questions about what we talked about last week? Like literally a week ago? Because we didn't have class on Monday. And I think most of you did not review the material on Monday because it's a holiday. All right, so we're going to talk about addition. Okay, so instead of me reading this stuff which you're supposed to read, okay, I'm just going to use some examples to illustrate the concept. Okay, just keep in mind, with a 1 unit class, you're supposed to spend 3 hours a week on that class. 1 hour of lecture time in class, 1 hour of prep time or homework time before, and 1 hour of study time after. So if you're taking 18 units, for instance, if they're all lecture units, you're supposed to spend 54 hours a week on your classes. Does that mean that you actually have to spend that much time? Well, it depends, right? Some people can, if this is what you like, and this is also where your, what's the name of that word? Aptitude, yes, talent, but aptitude is, you may not need to spend that much time. On the other hand, some people may need to spend more than 54 hours to take 18 units. So how much time you have to spend is entirely up to you, but 54 hours or 3 hours per unit is the guideline. So I want everybody to kind of keep that in mind when you plan for your classes. Okay, so let's deal with addition. And what I'm going to do with addition is I'm going to use a spreadsheet, and not the same one that I used yesterday. If you want to watch the video for yesterday for the Tuesday, Thursday class, go ahead, that's fine. But I'm going to work on a new one today. All right? So we'll go ahead and go with a very concrete example. I'm just pulling a number out of my head right now. So let's say we are talking about 269 plus, okay, let me zoom in a little bit so this way you guys can see a little bit better. Okay, so 269 plus, let's say 772. There we go. Okay, and this is an addition. Okay, so I'm really trying to spell out addition even for base 10 at this point, because I want to point out a few really important mechanism when we perform addition. And the plus is on the wrong row. Let me put it back to the right place. There we go. Okay. And I will call this worksheet 2018-0905, which is today's date, cisp310. So this way you can find it in the shared folder. All right. So the first question is, what do I put here? Okay, so we have to think about this. In base 10, okay, which you're all familiar with, what is 9 plus 2? 11. 11 is one way to call that. But I will call it a 1 with a carry of 1. Because that's how we can perform multi-digit addition. Okay? And let me ask you another question. How do you know that 9 plus 2 is 1 with a carry of 1? I mean, seriously, how do you know that? Memorization, very good. Okay, so most of you have it memorized already. I don't see anyone, pulling out some Lego pieces. 9 plus 2, and then here's a 10. Oh, the quantity cannot be represented within, cannot be represented, less than 10. So you have to take away the 10, which is your carry, and then what you left is 1. Well, we know it because we have memorized all this stuff, but it doesn't mean that the concept is not important. So I'm going to write it this way. I will put a 1 here, which is the result, and I'm going to put a carry over here. So I'm separating the result of an addition from the carry of the addition. So those things are now separated into two pieces. The carry to the first or the least significant digit is assumed to be 0 at this point anyway. Okay? All right, so let's move on to the next column. 6 plus 7. 13, or we can call it 3 with a carry of 1. Okay, so now we say this is 3. Okay, the result is 3, but it has a carry of 1 to the next more significant digit. Is that okay? So I know this is not how we write down, when we do addition in longhand, but since I'm using a spreadsheet, I would like to emphasize, the carry, what is the carry. So I'm going to put the carry on its own row. Okay, last column. 2 plus 7 is 9. No problem. Okay, so now we have a second addition. The second addition is adding the, oops, I have to do this. So the second addition, okay, delete. Okay, so the second addition has to do with adding the result of the first addition and the carry of the column from its right hand side. Okay, now most of us, when we do math, we just put a little 1, right? The little tiny little 1 to remember there's a carry. I just use a big 1 here. So for those of you who insist, I prefer a smaller 1. Change the font. Okay, so for those of you who prefer, the carry should be written in a much smaller, font, then go ahead and just change the font from, say, 10 point to 7. There you go. Now you get your smaller one. Okay, so but there's a second addition. So with this second addition, 1 plus 0 is 1. That actually is the least significant digit of the sum. And then over here, we have 3 plus 1, which is 4. And then right here, we have 9 plus 1. So this one is tricky because 9 plus 1 is a 0 and a carry. Okay, so we have 1 carry here. So, but this is the end of a 3-digit base 10 addition. That last carry that we have here, we just kind of leave it hanging like that because it is a 3-digit addition. We can only have 3-digit numbers being added. They're called add-ins. And we can only represent a 3-digit sum. Okay, so the number of digits is already fixed. But it's not 41. I mean, it's 1041. Well, we can't really represent that 1000. We just have to say there's an overall carry of 1. And that's the best we can do. Is that okay? So not quite the same as how you would normally do addition, because you want that 1 to be represented as 1,000. But when you have fixed width addition in a computer, then you can only say, we are only using 3 digits for the numbers to be added as well as the sum. But the overall carry is on its own. It can be a 0 or a 1, but it is separately represented. Are we still doing okay so far? So somewhat familiar, with what you normally do things, and a little bit different in some other ways. Are we good so far? All right. Okay. So what I'm going to do next is I'm going to introduce a table. Okay, I can use a separate sheet for that. And I'm just going to have x here. I'm going to y here. And this is called, the result of x plus y. I'm using this notation rxy to represent that. And then this is the carry of x plus y. Okay? So as we have seen already, 6 plus 7 has a result of what? The result is a single digit, 3, and a carry of 1. Okay, so you can kind of imagine if I really want to spell out this table, it's going to be pretty long for base 10. How long is this table for base 10? How many rows are we talking about for base 10? Counting all the trivial ones. How many values can x assume? X is a single digit in base 10. So how many values can x assume? 10 of them, right? From 0 to 9. But y is an independent variable, which means the value of y is completely not depending on the value of x, which means for every single value of x, y can go from 0 to 9 as well. So how many rows are we talking about if I want to spell out this entire table? 100. 10 times 10 is 100. Okay? So I'm not going to do that. Okay, well, it's actually pretty easy to do it because I'm using a spreadsheet. But I'm not going to do it, just because, it's, well, might as well do it. I want to show you how, why spreadsheets are so useful, and that's why I'm doing this. Okay, so we start with this, and the result of the addition, can someone tell me how I can compute the result of a single digit addition using operators that you have already learned in C and C++? And I tell you this is base 10. Okay, that works. You can use a ternary operator, and that thing does exist in the spreadsheet as well, but there's an easier way to do it. What you said is right, okay? But there's another operator that we can use without any comparison. It's like, yep, this, and then that will always give us a single digit result in base 10. Mod 10, very good. So we're going to use a mod operator here. So we say it is a mod operator. What we are doing is we are adding this number and this number. Whatever the sum is, I'm modding it with 10, which means I'm looking at the remainder of the sum divided by 10. Okay? What about the carry? Is there a way for us to find out the carry of x plus y? X being a single digit, but it can go from 0 to 9. Y is a single digit from 0 to 9. This time, I'm only interested in, is the addition going to result in a carry of 0 or a carry of 1? What kind of operator are we going to use? It's a good buddy of the mod operator. It's the more better known, buddy of mod. Mod involves division, right? So division can help. So you use the sum, x plus y, you divide it by 10. And then you get rid of the fractional part because that's not useful to us. Sorry? Yep, you can floor, get rid of the fractional part. Now, if you do this in C and C++, there's no need to take the floor because in C and C++, integer division is automatically only looking at the integer part of the division result. But a spreadsheet, on the other hand, is always dealing with floating point numbers. So that's why we have to take the floor. Okay, so that means that this is the floor of, once again, this x here plus this y here. So I'm using cell designation to refer to values of other cells, and this is the power of a spreadsheet. Is the value of one cell can be based on the calculation of doing something with other cells. Okay, and I forgot some parentheses because I need to do a division to the sum. So that means I need to put a parentheses, open here, close here, divide the whole thing by 10, and that's it. All right. So some of you guys may say, oh, so you're going to do this 99 times now? Not quite. So I need to figure out a way to move on to the next one here and move on to the next one here. What would be the best way to do it? Okay, I think I got it. So let's say x is the one that changes only once after y changes 10 times. Okay, so what I'm going to do here is to rely on the row number, because these row numbers are off by just 2, so I can use the row number as a part of the equation to figure out what x should be and what y should be. Okay, so the first thing is to refer to row. Okay, this is the row number. So the row number for row 3 is just 3, which is not what I want, right? So I take this row number and I go like, okay, let's subtract 2 from it first, because that is actually the number that I really want to work with. And then if x is going to stay 0 for 10 rows, and then 1, and then 10 rows, and then 2, and then 10 rows, then I'm only interested in the tens of the row number minus 2. Okay, so to extract that, I divide this number by 10, and that's going to be a fractional number, which is not what I want. So we take the floor of that, and I think it meets one close parenthesis, and that's it. Okay, what about this guy? This guy is going to change every single row. So it goes from 0 to 9, 0 to 9, 0 to 9, like that. In other words, if I look at the row number minus 2, this one should be 1. Okay, and that's proper. But this one is also going to be 1, and no, this one is going to be, let's see, this one's going to be a 0 right here. This one's going to be a 1, because I want that pattern to be repeating. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, and so on. So the mod operator is perfect for that, right? So I look at row number minus 2, which will give me a sequential number offset by 2. And then I take that number, I mod it by 10. That will give me a repeating pattern of 0 to 9. Okay, so we look at this and go like row. Okay, so this time it's a mod operator. We take row minus 2 and then mod it with 10. And here's the 1. These two are already in equation form, which means I can just copy these over here. Now I can take all 4 of these, shift click will select multiple, and then I just have to drag all of this down to 102, okay, row 101, sorry, 101. So we just drag it all the way down to 101, release, and we got the whole table. Woohoo! Spreadsheets are fun. It's more fun when it saves you a lot of work. Okay, so I can drag this bar down. Okay, there we go. So this way, I can have the first portion, the first pane of the sheet, only looking at row 1, and then I can scroll the rest. So this way, I can always look at the header of a column and know what we're talking about. Okay, let's spot check, right? I mean, just because I made some numbers appear on the screen doesn't mean they're right. 5 plus 8 has a result of 3 and a carry of 1. Does that make sense to you? Okay, let's try this one. 6 plus 3 is 9 with a carry of 0. All right. So this is the table that you have memorized, okay? And how much time did we use to memorize this? Pretty much first grade, okay? So we spent the entire first grade just memorizing addition and subtraction. Is that okay? All right? But when you look at the equation, okay, so when you look at every single equation in this entire spreadsheet, everything that says division by 10 or mod 10, division by 10, division by 10 and mod 10, that 10 is nothing more than the base that we are dealing with, okay? So if I want to change this to base 7, I just have to change all the 10s to 7, and it becomes a table for addition in base 7. Is that okay? All right? Oh, if I want to figure out base 2, I just have to change that base to 2. Then the whole thing should work exactly the same way. Does that make sense? Maybe? Well, let's give it a try, okay? Let's give it a try and see what kind of a table it's going to give us. I'm not going to destroy this one. I'm going to keep this spreadsheet. So I'm just going to make a copy somewhere else. So I'm going to need I only need to copy the first 4 cells. Control C, open another sheet here, and Control V and paste it here. All right, so now I just have to go here and then change all the 10s to 2 because we are dealing with base 2. So here's a mod 2, and here's a division by 2. I should have made it refer to another cell just for the base, so that way I don't have to change as many cells myself. There you go, 2. Basically defining a constant, when you're thinking about programming. Okay, I think that's all we need to change because the rest I can just copy and paste. There we go. And then select this whole thing, copy it. All right, so I claim that this is the addition table for base 2. Well, the other table worked for base 10, okay? And 10 is the only constant that makes it a table for base 10. So to change the table to work with base 2, all those 10s will change to 2, and they should work now in base 2. Let's see if this makes sense. In base 2, 0 plus 0 has a result of 0 and a carry of 0. Does that make sense? Does it really depend on the base? If I use base 13, would that make any difference? Nope. What about the next row? 0 plus 1 has a result of 1 and a carry of 0. Makes sense in any base. 1 plus 0 is 1. The result is 1. The carry of 0. Does that make sense? Yeah. 1 plus 1 is the only one that's kind of tricky because the result is a 0 and it has a carry of 1. That is because the quantity of 2 cannot be represented by a single digit in base 2. Okay? It's the same situation that you get into when you say, what is 7 plus 3 in base 10? 7 plus 3 in base 10 is 10 as a quantity, but 10 as a quantity cannot be represented by a single digit in base 10. So you go like, okay, so we're gonna have a carry. The carry takes away 10. What is left? Nothing. So that's why the result is nothing, 0. But you have a carry, you're basically asking the next more significant digit and go like, I can represent a quantity, and here, okay, help me. This is the extra stuff that I cannot represent. Go ahead and do it for me. So here's your base 2 addition. Pretty cool. But we are still using arithmetic operations here. So when you look back into the cells, you can see how we are using a mod operator here, which is basically division, but we only pay attention to the remainder. And this one is just a division too. So we are still using arithmetic operations. And we don't know how to do arithmetic operations in using transistors. Okay? All right. So now we look at this, and we'll focus on the carry first. So if you focus on the column for the carry, okay, which is this column here, and then you look at x and y, if you just look at this as a truth table, does it remind you of a particular Boolean operator or logical operator? Which operator does it remind you of? Logical AND. Very good. So it looks like ampersand, ampersand in C and C++, because false and false is false. False and true is false. True and false is false. The only time you get a true is when you have true and true is true. Okay, well, I claim that. Do you think the spreadsheet is going to agree with me? Let's figure out. So what we'll do now is we're going to say, this time we're going to use a logical operator AND, okay? And we are ANDing this with this, okay? And it's type sensitive. It says false versus true, but if I look at 0 as false, 1 as true, hey, these two tables are going to they're giving us exactly the same result, right? So why is that important? What is the significance of, this thing that's using a division and a floor gives us the same result as this column, which is only using a logical AND operator? Why is that important in this class, based on what we have talked about so far? What is special about AND? It's a logical operator. Can AND as a logical operator be represented by NAND gates? And NAND gates can be implemented by 4 transistors. Oh, so that means we can actually compute the carry of adding 2 binary digits using transistors. That is big, because now we have a way to say, we don't need division anymore. We don't need an arithmetic operation. We translate everything to logical operation. Well, at least the carry. Is that okay? That's the importance. Okay, so now we are left with the more tricky one, which is the R. Okay, so I'm going to put a column here. Insert 1 to the left. There we go. Okay, so this is done. Carry is done, because we can just implement it using X and Y. Okay, cool. This one is a little bit tricky. Doesn't quite resemble, if you look at the result column or column C, it doesn't quite resemble any operator that you have learned in C and C++, right? So this one takes a little bit more time to figure out. Well, but we do know that there are 2 rows in column C that have results of 1, and the other 2 rows have results of 0s, right? So I'm going to break this task down into a smaller task. Okay, so my first question is, let's not worry about the entire row or the entire column. Let's focus on just one single row of that column and go like, can I have an expression that gives me a 1 if and only if X is false and Y is true? Now, by the way, that's a trick question, because the question itself spells out the answer. I just realized it. Let me ask that question again. So this time, listen the question and see if you can figure out the answer. The question is asking, can I come up with an expression so that the result is a 1 if and only if X is false and Y is true?
It's kind of a weird one to be and.
It's going to involve and. So let's see if we can make it work. Okay. So it is an and. Okay, it's an and. Oops, an and. But we have to negate this guy first. So it is not X and Y. That gives us true. So I'm going to put it here as not X and Y. Are you guys totally convinced that not X and Y is true if and only if X is false and Y is true? the conjunction itself actually spells that out, right? But we want to make sure. So we're going to fill in the other rows of this column just to make sure that they're all false, because we do want to make sure that they are all false. Cool. Well, that takes care of one issue that we have to deal with. I'm going to have to insert 2 to the left here. Okay, so insert one more. There we go. So the other one that I want to deal with is this guy here. Can I come up with an expression? Once again, the question answers itself. Can I come up with an expression so that the expression is true if and only if x is true and y is false? X and not y. Very good. It's symmetric, right? So we'll go ahead and enter that. Okay, x and not y. And we'll enter the equation here. It is an AND operation. X is not negated, but y is. So that's y. Here we go. And then we replicate the equation for all 4 cells. Excellent. Why is that helpful? Because column D takes care of the first one of the result function. Column E takes care of the second one of the result function. But we can also see that for column D, it's true only for one particular row. Everything else is false. For column E, same thing. The only row that is true is the one that we're interested in, but everything is false. But tech, in column C, both of those rows are ones. Well, if I have one function to make one row true, another function to make only the other row true, what do I need to do to replicate what I have on column C? A logical OR, right? So now I use column F for that purpose. So I'm running out of space, so I need to kind of compact the other columns a little bit, just for representation purposes. So this way I can still fit everything on screen. There we go. Okay, so for column F, I'm going to say, oh, so this is going to be, I wonder if this will work. So let me see if this works. Concat. So it's going to refer to the content here. And, okay, I need parentheses. So it will have an open paren, the content of D1 as label of that column, close paren, the OR operator, open paren, close the literal string, and then the content of E1, comma, and then close paren again, and then close paren for the concatenation operation. Oh, it's concat. No, spell concat. There we go. Press the enter key. Doesn't like it. Raw number of arguments. Expect 2 arguments, but got 5. It doesn't like, like a variable number of things to concat. That's okay. I know how to fix that. It's just going to look really, really long. So I'm doing a concat here. All I need is just nested concatenation. That's all. And then I have another concat here. And do I need one more? Nope, I think that's it. 1, 2, 3, 3 concats. Can they do it? Nope. It's expecting it has 3, so that's 1. Oh, okay, I see. So between this one and the other one, there's one more concat here. Concat. That. Okay. There we go. And if you are asking that question, Tech, if you just type the whole thing, wouldn't that be faster? Yes. But that's besides the point. The point is to get this to work, not to make it look right. Let me say that one more time, because some of you may not have heard me right the first time. The point is to get this to work, not to get it to look right. To get something to look right, okay, have you guys prepared your resume? Some of you might have, right? So to line up the spacing and whatnot, there are a few ways to do it. The easiest way is to use the space character, right? I'm just going to put enough spaces before something so it lines up with whatever content is in the previous line. Well, that might work, but only for a certain font and a certain font size. The moment you change the page size, the width, or the height, everything doesn't look right anymore. They're all over the place. So the proper way to do that is to use tab stops, okay? Or use a table or some other way where it is much more flexible. You can change the layout of the page and it doesn't really move things around too much. Same thing here, it's just, I just want to do it in the right way and not just to worry about does it look right, okay? All right. Just me being kind of anal about this sort of thing. So now we have or between this and that. And then we extend it a few times. Whoops. Click. There we go. Woohoo! Look at column C versus column F. If I look at 0 as false and 1 as true, don't you think column C and column F are the same now? Now, the significance, once again, is if you look at column C, it involves a mod operation. A mod operation is basically a division, even though we are only interested in the remainder. When you look at column F involves OR, which is a logical operation. Can we implement OR using NAND 2 gates? And we can implement NAND 2 gates using transistors. So this can be a hardware device, okay? But then you look at that and go like, but it's referring to things that are complicated because it refers to cell D2 and cell E2. So we look at D2, and D2 has a NOT gate and an AND gate. We know those things can be implemented using NAND 2 gates already. So the bottom line is column F, or the expression of column F, can be implemented using transistors. Yes, we are talking about a lot of transistors, but nonetheless, transistors. That is the significance. So now we are done, okay? By using column F and column H, ignoring column G and column C, D, and E, we now can compute the result of a binary addition as well as the carry of a binary addition without using arithmetic operations and only rely on logical operators. That's huge. I'm kind of surprised that you guys are kind of like, okay, if you say so. This is huge because we're making a connection to all the way back to the topics of the first class. I can use relays to do this. I can use vacuum tubes to do this. I can use transistors to do this. The idea is it only relies on certain kinds of valves. And there's no arithmetic operation. Arithmetic operations is now implemented by Boolean operations that you already know. And that's why I chose to use the notations that you already know in C and C++, because they are the same. Is that okay? All right. Now, what we will do next is we're going to look at, multi-digit addition, and then we'll try to figure out, okay, so now we got the R, we got the C. How do we use these things to actually do addition? Because this is a very simple mechanism. So now, what I'm going to do is I'm going to introduce, this is x0. Okay, in the notes it's x subscript 0 or x in bracket zeros. And this is x1, digit 1, and this is x2, which is digit 2. And down here we have y0, y1, and y2. Okay, and this example does not even only pertain to base 2. It actually works on every single base. Okay, all right. So what do I put here? Okay, clue. I only have to choose between R and C, okay? So in the previous example, what do I put here? Do I put the C, the carry of something, or do I put the result of something? The result, okay. So this is the result of x0 plus y0. Okay, it's just a notation of how I do it. So what I'll do next is I'm going, because if you can kind of imagine that this is going to be what? The result of x1, y1, the result of x2, y2, right? That's a lot of typing. I don't like that. So I'm going to call this q0. And over here, I define qi as the r of xi, yi. I mean, it's just a notation. Qi, by definition, is r of xi, yi. I is the variable. So when I is 0, then it's saying q0 is, by definition, r of x0, y0. Okay, it's just a shorthand because I don't like to type repeatedly. Okay, so this will become q1, and this will become q2. Cool. Is that good so far? And then down here, this is going to be k0. This is going to be k1, and this is going to be k2. And then we have to figure out what they are going to look like. Okay. Oops. Once again, I need to use quote plus. There we go. Okay. So down here, I'm going to ask what is k0. Well, you can't really define k0 using an expression. It's an input. Okay. So we just say it's an input. You know, we cannot know what it is. K1. How do we compute K1? K1 is the overall carry from column E. So let's see. It can be the carry of x0, y0, right? If x0, y0 as digits of the numbers to be added is more than the base, or more than or equal to the base, then we have a carry that we now represent as K1. Does that make sense? Okay. But wait, there's more. Just like those infomercials. But wait, there's more. This Q0 plus this K0 can also give us a carry. Think of the case where x0 is 5, y0 is 4. 5 plus 4 is 9, so Q0 is 9. Okay? But what if K0 is a 1? Well, 9 plus 1 is 10, so even if we're dealing with base 10, it will still have a carry to K1. Right? So that means I have to add something to K1. So this can also be the result of a carry when we add Q0 to K0. Is that okay? So if you have any questions, now is a good time to ask, because this is the format that I explained addition and subtraction a lot. So if you have any questions about the notation, what each symbol is representing, now is a good time to ask. So are there any questions? Nope. Okay. What do you think K2 is going to look like? About the same, right? So K2 is just going to be about the same, C of x1, y1, because it's one column to the left, C of Q1, K1. So once again, because I'm lazy, I don't like to rewrite things that have a certain pattern to it, so I just say Ki. Okay, so I generalize to Ki, where I is the column, goes from 0 to 2 in this case. So it becomes the carry of x I minus 1. Okay, this time I have to use square bracket to indicate that I minus 1 is the subscript. Y square bracket I minus 1 plus C of Q square bracket I minus 1, and then K square bracket I minus 1, just like that, where I goes from 1 to 2, 1 to 3, excuse me. I goes from 1 to 3 in this case. Is that okay? So what I'm doing here is I start with a concrete base 10 addition example, just so that we remind ourselves how it is done. Then we move on and talk about, oh, but what about the R and the C function? Oh, we can generate a table in a spreadsheet to tell us this plus this has a result of this, carry of that, okay? And then we change to base 2, okay? About the same concept, except the table is a lot smaller. And now we look at a 3-digit by 3-digit addition in a very abstract way, okay? Instead of using very specific digits here, I'm just saying, how do you come up with this digit over here? Oh, we apply the R function. How do you come up with the carry over here? Oh, we just have to combine the result of 2 carry functions together using an addition. That becomes the K bit. Yep.
So K1 you're putting as the result of the carry from the least significant digit there?
Yep. It's the result of adding these two. It's the carry of adding these 2 bits and adding to it the carry of adding these 2 digits. Because both of them, okay, let me choose the term carefully. Because up to one of them can contribute to the carry. Only up to one. Okay. All right. So are we okay so far with everything on the board right now? Okay. Is everybody connecting how this relates to everything else that we have talked about today in the other sheets of this same spreadsheet? Yes? Okay, because if there's a disconnect, now is a good time to say, well, I don't really see how this relates to, and then whatever concept. So are we good? More or less? Okay. Well, I have a problem because this is an arithmetic addition. We can boil everything down to Boolean when we're dealing with base 2. R boils down to Boolean just fine. C is even easier. C itself is just conjunction, is and. Okay? But now we have this arithmetic addition here and this arithmetic operation here. So we go like, that's not good because we want everything to be Boolean. We want everything to translate to logical operators. So now we look at this and go like, is there a logical operator that's close to addition but not quite? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. Okay, so which logical operator comes pretty close to doing that, but it misses one of the results? OR, very good. So logical OR is pretty close. So let's look at those 2 operators. So we have X, we have, okay, let's not use X because it's confusing to use X here. S and T, there we go. So no, I don't want to use S and T either because S is sum. So we'll choose another term. A, B, yeah, A and B would work. Okay, so we have A and B, and this is A or B, and then this is A plus B. Okay, so what I want to illustrate is how close it is. So A is 0, can be 0, 0, and then we have 0, 1, and then we have 1, 0, and then we have 1, 1. Okay. So if you're talking about the logical operator, the OR, then we get 0, 1, 1, 1. Any questions about the logical OR column? Is that good? Okay. When we look at the actual arithmetic operation plus, then we get 0, 1, 1, and 2. We got so close. Then we go like, how are we going to deal with that? Wait, if this condition never happens, then we don't have to worry about the last row because if it is not possible that both of the C functions returning a 1, if that is not possible, then it is okay to use OR in place of plus. Is that making any sense? Okay? So now we have to think about it. Go like, can we prove that? in other words, okay, let me make this bigger, and then I will highlight which portion we are referring to. So we'll focus on just a portion here. Okay, so let me see if I can do this. Okay, so let's say this is returning true, okay, or returning 1. Under what condition is this portion, the highlighted portion, going to return a 1? Remember, carry is the same thing as a logical AND. So under what condition can it return a 1? And if they're both true, yes. So you're talking about x I minus 1, y I minus 1, both being 1s, right? Okay. What is the implication of that? If both x and y have bits of 1, what happens to the q? What is the definition of q? It's out of here because I zoomed in. But what is the definition of q of I minus 1?
Binary that make it a 0.
It-
That's the carry.
It's the r. Q is basically the result of the r function, okay? And the r function says the r function only returns a 1 if and only if one side is a 1. Is that okay? But by confirming that the carry function of x and the y bits are both is 1, that means the q is going to be a 0, doesn't it? Yes? All right. So if the q bit is a 0, it doesn't even matter what the k bit is, right? Because in the only time a carry function can return a 1 is when both parameters are 1s. If I can guarantee the q bit is a 0, the carry function is going to return a 0. So we have one problem solved, okay? If the left-hand side is true, we know the right-hand side cannot be true. Okay, but that's not done yet, okay? Because we also have to prove the other way around. So we have to go back and now say, okay, what if we confirm that this is true? Can we say that if this is true, the other side has to be false? Well, same constraints, okay? The only time the highlighted portion here can be true is the q bit and the k bit are both 1s, right? Wait, if the q bit is a 1, what does that mean? It means one and only one of the x and y can be true. The other one has to be false, right? Oh, so that means it doesn't really matter which one is a 1 and which one is a 0 because the first carry function cannot return a true. It has to be false. Is that okay? So now we prove, okay, this is actually a very informal but nonetheless a mathematical proof to say that you cannot have a situation where both carry functions are returning 1s. This is handy because that means we can use logical OR in place of addition because the last row, the row 4, never happens. Is that okay? So the significance of this discussion is we can now have a general equation for the carry so that instead of using a plus here, now remember this only works when we are dealing with Boolean or base 2, but nonetheless, we can now do that. So now everything can be done with logical operators, which translates to P and N transistors. We can now perform addition, not using any arithmetic operations and only rely on logical operations that we already know how to implement using transistors. That is huge. I mean, this is really, really significant because we have just reached another milestone in this class, where we go like, oh, we can actually just use logic gates to do quote unquote computation. We can add. That's big. It's important. Is that okay so far? Okay. All right. So if you're wondering where in the notes we are referring to, I'm just reading, in the sequence, in the same sequence as it is presented here. So all of this stuff that I just talked about, they're all in binary number addition. Okay, so let me go into the notes here and tell you where we are at. So we are basically done with blah 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 dun 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 dun. So we are now at this point. We are right before section 6 already in this module. Now, section 6 is actually incorrectly titled. It really should be saying, but wait, there's insert here a lot more. Okay, there's a lot more. So what we want to do is to kind of read the first paragraph. Okay, so the first paragraph reads, because the ki digits are defined explicitly, the overall design of an adder is quite structured because ki can be used to compute ki plus 1. Okay, so let's go back to the equation and just take a look. Okay, the equation is in the spreadsheet and it is right here. So when you look at the definition of ki, okay, just to be consistent, I can add the square brackets back to here. Okay, there we go. So you can see how k bracket I can be computed using x, y. Okay, those are easy. Okay, the x and the y bits are presented first to the adder because they are the numbers to be added. Okay, so we don't have any problems getting a hold of the x bits or the y bits. Not a problem. The q bit is easy to get to because once you have the x and the y, the q bits is really just a constant time calculation to get to the q bits. So we don't have a problem with that either. The problem that we have is it relies on k bracket I minus 1. In other words, until k bracket I minus 1 is done, I can't decide ki. Until ki is done, I cannot determine ki plus 1. Until ki plus 1 is done, I cannot determine ki plus 2, and so on. In other words, there's a linear dependency all the way back to k0. Is that okay? Well, that's not good. It's not good because this means if you know how long a 32-bit adder is going to take to finish its calculation, a 64-bit adder is going to take twice as long. A 128-bit is going to take 4 times as long as a 32-bit adder, and so on. It's linear to the width of the numbers that we are adding. And that is not acceptable. It's not fast enough. So how do we fix that problem? Well, the way we fix that problem is we look at the math of this whole thing and say, can we remove this dependency? In other words, can we express k arbitrary I only using the bits that we already know? Okay, the x bits, the y bits, easy peasy. The q bits are pretty easy too. And can we just do that? Because if we can make the computation of ki only relying on the x bits, the y bits, potentially the q bits, and maybe k0, because k0 is also an input bit. It's always available. Then we have a fast way to do addition. Is that making any sense? Okay. So hold on to that thought because I'm going to finish this table first. So we are missing one single row here. The last row would be the sum bits, the actual sum. S0, S1, and S2, they're representing the individual digits of the sums. So what do you think Si is going to be defined as? The clue is right there on the projector. It's the result of adding Qi and Ki. So we add xy, we get to q0 as the result, and it can potentially contribute to k1 as a carry. And then we add q0 and k0 to get to the sum. Okay? So once we have the k bits ready, the computation of the actual sum is pretty easy. Okay. So the carry bits is going to be the biggest problem that we have to deal with because it seems to have a linear dependency. Ki depends on ki minus 1, ki minus 1 depends on ki minus 2, and so on. So how do we break this chain dependency? So in the notes, there are several steps to it. So the first step, which is a long, I wouldn't say long, but it is a mathematical proof, right here. Okay. This is Boolean algebra. Okay, I'm not expecting you guys to be able to prove theorems using Boolean algebra, but once I explain it, I really hope that you guys understand it. Especially if you're going to take cisp310 from me, because I do about the kind of same thing in 440, except in 440, my students actually have to prove theorems using Boolean algebra. Okay, so let's see if we can. Does the first row surprise you at all? It's defining ki plus 1 to be, so in this case, the plus actually means or, multiplication actually means conjunction, and then the exclamation point is negating whatever is immediately to its right-hand side. Is that okay? So given that notational difference, does the first row surprise you? No, it's the kind of same thing that we have talked about. Except in the spreadsheet, I express ki using xi minus 1, yi minus 1, qi minus 1, and ki minus 1. By shifting the index by 1, I have this definition. So the first row should not come as a big surprise. How did I go from the first row to the second row? And this is only for base 2, by the way. The conjunction is, how did I turn the carry function into just a simple conjunction? Do you guys remember that we talked about that table? The only time you have a carry is when both inputs are ones. So a conjunction would do the same trick. Okay, so that's how we got from the first row to the second row. How did we get from the second row to the third row? How do we go from this row to this row here? It's the expansion of qi. Qi, by definition, is the result of adding xi and yi as bits. Is that okay? So that's really just expansion by definition. And then from the third row to the fourth row. So the only difference between the third row, which has the result function, and the fourth row, which has this weird thing about xi and not yi, or not xi and yi. What is that doing? It's doing the result, or we also know it as exclusive OR. Okay. What about from the fourth row to the fifth row, from here to here? This one you should be familiar with even in arithmetics. We call that distribution. Very good. So as it turns out, distribution also works in Boolean algebra. Okay, and it actually works in both ways in Boolean algebra too. But nonetheless, if you really look at plus as plus and multiplication, that's the same kind of concept. Okay. All right. So getting down to the next one. So we go from here to here. The only difference is the introduction of a true that is ANDed or conjunction with xi, yi. Is that okay with you? If I say, x, is that the same thing as x and true? How do we know that? Yep, exactly. Yep. You can use a truth table to prove that. Okay, very good. So by introducing this one, other than making the expression a little bit longer, doesn't really change the value. Okay, it's the same thing as in multiplication. If you say blah, 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 and then blah, blah, blah times 1, the times 1 doesn't really do anything, right? So from here to here, it's a little bit tricky because you have to remember the plus is disjunction, is OR. So the question now is, is true the same thing as true or something? What do you think? Yep, exactly. Because with an or, if at least one side is true, the whole thing is true. So that means one or whatever is always true. In other words, I'm making this unnecessarily complicated, but I didn't change the meaning. I did not change the value. I just make it a little bit longer, that's all. Okay? And then I use distribution again. In other words, I take this expression and I distribute it to this. If you look at the end result, all I did is I artificially introduced a term like this that was not there before. Okay, if you look at this row here, this term was not there, now it is. But it doesn't change the overall meaning of the entire expression. It's just, hey, now we can express it with some junk, but it's not really changing the meaning of the entire expression. Okay? From here to here, I am replicating. So you can see how this term is here, and now it is also here. Now remember, plus is not addition. Plus means disjunction. So the question is if x is a Boolean variable, is x the same thing as x or x? What do you think? When x is true, true or true is true. When x is false, false or false is false. So by using a disjunction with itself, you're not changing the value. You're just going like, oh, okay, we can just add more term to the whole thing, but it doesn't change the meaning. Okay? So by adding this term and replicating over here, I'm just making the thing more complicated. It looks more complicated, but it really has the same value as it had before. Okay. So from here to here, all I'm doing is association. Okay, I'm changing the order or explicitly specifying the order. Do this first, and then do this first before the rest of the disjunctions. Okay, and by doing that, I allow myself to factor this into this. I also factor this into this. This is factoring, which works pretty much the same way as regular arithmetic factoring. Is that okay? It's the opposite of distribution, basically. Okay? So now, from here to here, we have yi or not yi. We don't really know what yi is. Yi is one of the inputs. But if I look at the expression yi or not yi, that guarantees to be a 1. Is that okay? Because we are looking at a variable and its own negation. If the variable is false, the negation has to be true. If the variable is true, then it's okay. The negation can be false because we have the true already. So that's why I combine the y or not yi to true, the xi or not xi to be true, and then the true is just canceled. It's just simplified because it doesn't have to be there. So now we end up with this, and then one more factoring gives us xi, yi as its own conjunction term, xi or yi as a disjunction term, and then the whole thing conjunctioned with ki. Okay? So no, don't worry, you don't have to derive anything like this in this class. But I like to convince myself and you how we can go from ki plus 1 to this final form. Is that okay? So the next part of the notes basically just has some additional definitions. So by definition, gi is xi, yi, the conjunction of xi, yi. And then pi, by definition, is the disjunction between xi, yi. Is that okay? That's just how it's defined. All right? So let me clarify all these numbers, all these letters that we have introduced up to this point. Okay? And I'm going to use, I'll use this. Okay, clear this out of the way. Okay, so x and y are inputs. Numbers to be added. Okay? So xi refers to a particular digit in x, yi refers to a particular digit in y, and so on. Q is basically what I call a partial sum by only adding digits of x and y, but not worrying anything about carrying. Okay? So it doesn't include carrying. K is the row of carries. Okay? S is the sum. And then P, by definition, is X, I, or YI, so PI. Okay, and let me make it more clear. And then the last one is GI. GI, by definition, is XI and YI. So in the simplified term, I've just used multiplication to represent conjunction. So those are all the terms that we have introduced. Okay, X, Y are introduced. K0 is an input, so that's the only special case of the carry. Q is the partial sum, not partially, but partial. So Q is the partial sum. S is the actual sum. The GI and the PI term are only here to help us with what we're going to do next. So are we okay so far with all those letters? Okay, which ones are the inputs? Which one have a very simple definition? It's like, oh, okay, this is by definition, so that. Okay. So what we're going to do next is to go like, okay, well, our objective is try to express Ki only using things that are quick to compute and not Ki minus 1. Okay, that's our objective. So we want to see whether that can be done. Now that we have done all of this gyration, it doesn't seem to be very helpful. Okay, so let me get to this point here. Are there any questions about this one? Not by definition, but using the definition of GI and PI. I'm just looking at this and go like, hey, XI, YI is now known as GI. XI or YI is now known as PI. So I just make it easier to write. That's all. Okay, so we are not deriving anything. We are just saying, oh, we have these handy definitions here so that Ki can now be, Ki plus 1 can now be expressed simpler, using simpler terms. Okay. So the first thing we need to do is to say, all right, well, if that is the case, what is K1? Oh, K1 is easy because there are no lower or less significant bits in this case than K0. So when we hit K0, we are done. Okay? G0 is easy to compute because it's just the conjunction between x0, y0. P0 is easy to compute. It's just the disjunction between x0, y0. So K1, pretty quick to compute. Not a problem. So we now look at K2. So K2 looks a little bit more complicated because the first row says, okay, so we're going to use that definition earlier. So K2 is now expressed as G1 or P1 and K1. Darn it, we don't like K1, right? How do we get rid of K1? Substitution. We already know how to express K1 with K0. So we take this definition, we expand it here, and then we do the distribution. Now we can express K2 without referring to K1. Is that okay? But this looks complicated. It's got like the conjunction of P1, G1, the conjunction of P1, P0, and K0. Those are all fast to compute, okay? Because all the P and the G terms only rely on 2 input bits, right? And then we just have to do a conjunction of those things. Yeah, easy peasy. What about K3 then? K3 is down here, okay? Same approach, okay? The first thing is we expand K3 into G2 or P2 and K2 using that general equation earlier. This is no good. We don't like K2 when we want to express K3. Fine. We just derived K2 earlier, right? So what we do is we take the definition of K2 earlier and expand it here. Distribution, bam. Now we can expand, we can now express K3 only using the P and the G terms and K0. What do you think K4 is going to look like? Kind of the same thing, but a little bit longer, right? So there's a pattern to this, okay? So the pattern that we are observing is now captured in this notation. Now, the big V and the big, the big disjunction, the big conjunction notation is really just specifying a series, okay? It's nothing, it's really the same thing as a sigma notation. Is that okay? So this term here, okay, let me use a mouse pointer, so that's going to be recorded as well. So this term here is really just saying, if I know what I and n are, I'm just looping, okay? J is a loop variable to go from I plus 1 to n, and this is just a huge conjunction of all the pj terms. Is that okay? Take this thing as a function, okay? And make I a outer loop variable. So I goes from 0 to n. So each term of this entire bigger disjunction is g of I, okay? I is in the outer loop. And this big mess here, whatever that big mess turned out to be. Is that okay? So that means this part, if you want to use a machine or program to come up with, to expand all of these terms, this is done by a double loop. Okay, one inner loop to take care of the conjunction thingy, and then the result of the conjunction thingy is ended with the gi, and then you have the outer loop to loop through the i's. Okay, so it's not, it looks really kind of ugly, but when you think of this as a for loop inside a for loop, it's not that difficult to understand. So you have this one big huge mess, and then you have a smaller mess on the other side. So the smaller mess on the other side is dependent on n. So n has to do with which carry bit are we trying to figure out, okay? So kn plus 1 is the carry bit that we want to figure out. Once we know what n is, then I goes from 0 to n, and then you just pull all the pi terms and then do a big conjunction with those pi terms. And whatever this entire thing is, and that with k0. And that becomes the single term that's kind of on the side. Is that okay? So if you're working for Intel or AMD, and your boss says, I want you to generate the logical expression for the carry bit 64, okay? In other words, n plus 1 is 64. Are you going to do it by hand and express K64 as, G63, or, expand it by hand, and then, now I need to figure out what is K63, expand it, now we have to figure out what is K62, all the way down to K1, and then take the result of K1, plug it back into the equation of K2, expand it, take the K2 expression into K3, expand it, and then work your way back up to K64. If you did that, you will be fired. So what are you going to do if that is your job? Your job is to generate the logical expression for carry 64, the 64th carry bit. What are you going to do? You look at this, and then you use your favorite scripting language, okay? Can be JavaScript, can be Perl, can be Python, can be PHP, doesn't really matter. Write a double loop here and a single loop over here, generate the whole thing, you're done. The next day your boss comes in and go like, oh, you know what, AMD, our competitor, is doing 64-bit adders. We have to do 128 bits. Can you get it done? And you say, I'll get it done in a day. So you go into your program, you change that constant 64 to 128, you run that program, get it done in, 5 milliseconds, and then take the day off. That is the power of abstraction. Okay, by abstracting and understanding the pattern behind things, now you can have algorithms to do the work for you. So are we okay so far with this? Because I went a little bit further with this class than the Tuesday, Thursday class. So at the same time, I'm thinking, well, did I kind of go over stuff a little bit too fast? Any questions? Yep.
What's your YouTube channel name?
Some profs. Yep, it's SOMEPROFS. There's a reason why I'm not putting this into the projector. Because if you're looking for the channel name, you wouldn't be watching it in the first place. Yep.
So we have so we've made addition into a logical or using logical operators.
Yep.
How do we turn a loop into a logical operator?
You cannot. Okay, so loops are a little bit special because there are gates or there are designs where it looks like there's a loop. Okay, the output of a gate goes back to the earlier gates. Something like that. We'll see that later. In the form of a flip flop. Okay, nothing to do with walking feet and stuff like that. But it's called a flip flop. So those look like loops, but they don't really do what we are trying to do here, which is looping through a particular counter, right? So to understand how to loop, in this particular sense, you need to understand clocked logic, synchronous clocked logic, which we will do. Okay, it's just not yet, but that's a very good question. That's also how I grade your assignments. When you turn in a Logisim file, I actually have a mechanism that goes through quote unquote a loop that feeds test cases to your logic and look at the result of your logic and compare that to the actual correct answer. So there's that. So we'll talk about that later, but that's a very good question. How do we do loops, quote unquote loops, in logic gates? So it relies on the concept that we have not talked about, which is synchronous or clocked components. Anything else? So we do have a lab activity today, over in the lab. Shouldn't take too long. It's about multi-bit gates. Okay, so when you think about a gate, you think about a gate as, oh, here's one input bit, here's another input bit, and here's the output bit. Okay, a multi-bit gate is going like, oh, this pin, okay, is a multi-bit pin. This pin is also a multi-bit pin, and then the output is also multi-bit. It translates basically to bitwise operators in C and C++, where bit 0 of the output is the conjunction of bit 0 of the input of the input. Bit 1 of the output is the conjunction of bit 1 of the inputs. Bit 2 of the output is the conjunction of bit 2 of the inputs, and so on. Okay? The idea of doing that is some of these calculations can be done easily with a multi-bit gate. Okay? Some of these cannot be done that easily. So the lab exercise is to set you up so that we will be able to simplify the logic so that we can actually implement a 3 by 3 bit carry look ahead adder. So we'll make our own adder using logic gates in Logisim. All right. So we have about 5 minutes. You can go to the bathroom, get something to drink really quick, and then we'll meet up at the lab at noontime.